Okay, welcome to the lightning talk session. The speakers have 5 minutes. I kick them off if they take long. Everyone good. Here we go.
Awesome. Okay, so my name is Clyde Alford, and I'm here to speak not about Python, but about Haskell, but with a perspective of what makes this language interesting for Python users. So, how many of you know about Haskell at all? Okay, so there's quite a bit. So Haskell is a purely functional programming language. It has a rich history. It's just about as old as Python, and it's a language that Python has already kind of like learned and borrowed a lot from. So you might be familiar with list comprehensions. That's something that Python pretty much took directly from Haskell. Things like the iteration protocol, generators, obviously functional features like lambda and closures and lexical scope. These are all things that Python takes from functional programming languages like Haskell and related languages. So it's already like a rich field that Python has borrowed from, so it's good to investigate. So one of the first distinctive features of Haskell is that it's lazily evaluated, unlike Python, which is strictly evaluated. So what this means is that you can, for example, have infinite data structures. Like here, you're actually defining an infinite list in Haskell, which is a lot like generators in Python, but it's actually a data structure that only gets evaluated as much as you use. So you can take 10 elements from this list. It'll only calculate those 10 elements, but the list is actually infinite. So you can keep on consuming it for as long as you want to. And it's not just like generators in Python, because you might think this is not impressive. It's just what you can do with Python generators. But in Haskell, everything works like this. So you can, for example, have an infinite tree. If any of you have a mathematical background, you might know the Stern-Brokaw tree. It's a way to enumerate rational numbers, but it's an infinite tree starting from a single node and just going infinitely in all directions. And this is an example of it, where this is now cut off to 3 levels, but this whole tree actually goes on infinitely. You can write tree traversal algorithms that work with this tree just as if it's actually all there, but Haskell will only evaluate what you actually use. So, the second thing that comes up with Haskell that's different to Python is that there's no side effects. This is what's meant with Haskell being a purely functional language. So instead of side effects, you have first-class effects. So you might know in Python, many things are first-class, but effects aren't. In Haskell, an action like doing getLine or printing something, these are actually I/O actions, which are values which you can manipulate and pass around and combine, just like any other effect. And there's an example of like defining some effects, composing them together, and then at the end there, taking an effect and replicating it 5 times. It's just like you would replicate something 5 times in a list. And there's like a whole way of working with effects that you don't really often get in Python. There's some libraries like this, but it's a really cool part of Haskell. So at the heart of Haskell is algebraic data types. This is another thing that Python has relatively poor support for, but that Python can actually really use. Now, algebraic data types in Haskell are really core. It's like you define a data type in terms of its constructors, and you define computations in terms of how they destruct this. So you have this duality of construction and consumption, which drives the evaluation of Haskell programs in a really beautiful way, which you can't really express in Python very well or very clearly. It's like this yin-yang loop. In Haskell, even though it's a strongly typed language, you can actually, a lot of the time it feels like working in Python, where it's very loosely typed. Where Python has duck typing and interfaces, which you're all familiar with. In Haskell, you have type classes which express certain abstractions. Like, there's an example of a number where you have a certain interface, you have different implementations for different types, and you can have generic functions across this. So you can write generic code and polymorphic code without actually caring too much about the details, much as you would in Python. So you can see these are some examples of type classes in Haskell. You can see they do pretty much the same thing as Python does, with magic methods, with the double underscore functions, with the protocols that Python has. But in Haskell, these are first-class concepts which you can do a lot more with. One of the cool features about the Haskell type system, which a lot of people don't appreciate, is that it's not a bondage and discipline thing. It's a way of actually proving things about your program, expressing your problem domain in a way that makes more sense for your program. So here's an example of where you can take, let's say, a built-in type like double and refine it to Celsius and Fahrenheit. And you can make unit conversion explicit so that it's impossible for you to mix up your units. And this is something that you can't easily do in Python. But in Haskell, you can express this, and you can make mixing up your units a compile time error with no runtime cost. It's like all of this happens purely at compile time. And it doesn't stop there. You can actually do type-level programming in Haskell, which is another thing that I would really like to see in Python. You can encode things like algorithmic invariance. If you're familiar with red-black trees, you can have the red-black tree balance condition encoded at the type level so that if you mess up your algorithm, you get a type error, not a runtime error. You can encode things like business logic, like checking whether strings are escaped, whether users are logged in or not at a certain point. You can make those type level checks instead of runtime checks. And this is like a really amazing thing that you don't even realize is possible until you've kind of like actually touched on it in this context. And then finally, lastly, just another example of the kind of like type level hackery you can do in Haskell. In the IRC channel, there's LambdaBot, and one of the modules it has is this thing called Ginny, where you can actually give it a type signature, and it generates an implementation of that type. Yes. And that's it. So, yeah, summary, Haskell is really cool, and if you like Python, it's a really cool language to check out. So, yeah, check it out.
Hello? Okay, cool. So I'm talking about PostgreSQL foreign data development in Python. So PostgreSQL is the most advanced open source database, the world's most advanced open source database. Foreign data wrapper, it's an SQL standard that deals with how database management system can integrate data stored outside of the database, right? So that's the actual standard SQL. Then Python is the world's most advanced open source language. Yeah. Okay, cool. So, what's a foreign affiliated table? So it's a storage engine which allows the user to create a table that is local representation of a foreign table. That's we can think of it as a transparent access method for external data. So, what data stays outside your database? So let's say you have some flat files, CSV files, log files, you see password. Let's say RSS feeds, emails, websites, APIs, directories, file shares, anything outside of your database, other databases and servers. Yeah, I'm just kidding about EC password. Okay, so you would actually like to, let's say you want to perform some SQL select statements on that database. So let's say select some data from an external data source. So Postgres allows this, and it also allows for rapid development within Python. Right? So there's a library called, or Python PostgreSQL extension called Multicorn. So it allows you to write foreign data wrappers in Python. So let's say you have something like this, right? You have a CSV file. It's called, and it's stored somewhere in temp. Why? Because Mongo. Let's look at Python. So you just have to instantiate the foreign data wrapper class. You have something over here called, you have your options over here, and then you have your columns over there. Then you have your execute method, which takes in your quals, your columns, and it yields on the line. Right, so you can have something else if you're parsing and logic and all sorts of things. So then you have to install the extension, of course, and create the extension. Then in PostgreSQL, you create the server, right? And then it also has to just point to some wrapper, which is your Python library space. And then your foreign table looks something like this. And then these are your options over here. You can pass in and you can use your options, of course, as seen earlier. And then you can just do a select star from your CSV, from your font table, and you can get your data in your Excel form. So, as you can see, the total line of Python goes about 44 lines, and your SQL is about 3 statements really. So what else? You can put your ORM on top of it, you can put your BI tool, you can put your kitchen sink above it, you can do one of those, right? If you have Postgres 9.3 plus, you can even do inserts, updates, and deletes. There's quite a few foreign data wrappers that are out there. There's foreign data wrappers that like to connect to SQL Alchemy, LDAP, Docker, even there's a PG OS query, which is basically like Facebook's OS query, but within Postgres. And then there's also the Redis foreign data wrapper, MongoDB foreign data wrapper, and there's much more on the PostgreSQL wiki. Okay, so how do you come about this? So yeah, I'm from SKSA, the control and monitoring team. What we do is our use case is that we have to archive our data to some files, and we archive it to like HTML5 files, and we have some legacy archive files to CSV files, which is like an internal format. So we query these files via a server. We use Postgres foreign data wrapper to represent it in the table. So it's time series data, and that's basically the form of it with the unique sample TS. So what we liked about it, it's an SQL interface, it remains the same, right? It's one interface for querying multiple data sources. So they should have file format and then have CSV format, and we also have the power of SQL, so we can do like other kind of reporting and things you would like to do. What I do not like about it, some writing some unit tests for the foreign data wrapper, it's a bit tricky sometimes. But you can get over that. And in the future, we actually plan to remove the HTML5 files and the other legacy files and then put some safe distributed object store within still created by the Postgres interface. So the interface remains the same, this SQL interface. And then your requirements for just basic selecting, just selects, you need Postgres 9.1 plus, you need the development packages, the Python development packages, Python 2.7. Or 3.3, and then also we are hiring.
be solved soon. There's a lightning talk at the end of the session where the video team will explain why this happened.
Briefly about VirtualEnv. Who's used VirtualEnv? Ah, fantastic. Talking to some of always talking. But yeah, every now and then I see my colleagues do that. Every time I die inside of it, because your package manager is going to cry because now suddenly you're taking over what the system thinks is your version of NumPy, and anything that gets installed by the system is no longer going to actually take effect. If you're really unlucky, it's actually going to overwrite what your package manager has done, and then your package manager will overwrite what you have done next time you upgrade your system. That's all not such a good idea. That tends to happen too. So what you should do is use a VirtualEnv, which on the show of hands, it sounds like most of you know how to do, is you create one by saying VirtualEnv and you give it a directory and it creates your virtual environment there. And then there's somewhere where it has an isolated set of packages completely separate from your system-wide packages and from any other VirtualEnvs you've created. So apart from being a good way to install newer versions of packages than your operating system provided, you can also test different sets of packages. If you want to check if you've listed all the dependencies that your package really has, you can make a very minimal VirtualEnv where you can install just what you say you have to install and see if it works. The second line is just what activates it and drops you into your VirtualEnv in your shell. The third line I tend to use, it's optional, but you're just upgrading pip and setup tools. The reason is pip and setup tools have moved a long way, they're moving very quickly, and I use Ubuntu 14.04, and they've moved on a long way since then. Some packages won't even install correctly without new versions. Wheels also good to install, because then new pip will build wheels out of packages installed and cache them, so that then next time you blow away your VirtualEnv or you have a new VirtualEnv, it can be much faster to install it the next time. And then once you've done all that, then you can install the packages you actually want to install and use. And that's all I have to say about that.
One, 10 cent mics.
How's that? Okay. So I just quickly want to tell you about the Center for High Performance Computing, and particularly astrophysics that we're doing there. We use a lot of Python for this. I'm mostly at the center, but I also have a position at the University of the Western Cape where I do astrophysics. So quickly about the CHPC, it's the National Supercomputing Facility, started in 2007, staff of about 30, 16 researchers supporting about 300 users around the country. Okay, so this is the place for researchers who need big computing to come to. In our new facility, there are over 24,000 cores. We have 5 large memory machines, some test-bed hardware stuff, some so-called big data facilities, big storage facilities, and it's ranked 121 in the top 500, if that's the kind of thing you care about. And we spent quite a bit of time on sort of training and development. So. Okay, so the users in many, many fields: health, mining, construction, energy, weather, film, finance, astronomy. Ask me about that later if you're interested. It's molecular modeling, there's bioinformatics, there's image processing, lots of simulation. But the kind of thing I do is more related to the square kilometre array. Who has heard of the square kilometre array? Who has not heard of the square kilometre array? So South Africa is spending 20% of our science and technology budget on astronomy. Okay, that's pretty interesting. So the Square Kilometre Array is a $1 billion telescope for after 2020, really. Starting being built now. So in phase 1, 200 dishes in South Africa, plus an array in Australia. But then in phase 2, there'll be antenna in 8 other African countries. Okay. So yeah, like I say, the first dishes are up near Carnarvon, and the first images have been taken. And you can see the 8 countries where the other antenna will go. So the SKA is a massive computing challenge. The SKA on its own, the data is more than 10 times our current global internet traffic. Okay, it's big data. Okay, but it's also a long time in the future. Maybe it's not so big then when you actually finish. And there are just so many levels of data crunching. So at the Center for High Performance Computing, we can tackle, we tackled some of those, not all of them, but particularly I work at these, at the sort of end there where we do statistical analysis of big catalogs of data, we do big n-body simulations so that we can do modeling. You know, there's theory and we've got data, and we need to do lots of modeling and stats in between to decide if your theory actually describes the nature of dark energy or whatever it is you're trying to probe. So the kind of astronomy projects we have, and I think we use Python for all 5 of these particular things. So Sean is in the audience. He has his PhDs in these exotic cosmologies and did lots of theoretical calculations. We also do these big simulations where we try and simulate big chunks of the universe and see if we can make galaxies that look like real galaxies. We do quite a bit of data mining, so we take all the data that's from satellites paid for by the rest of the world and extract interesting science. Then there's quite a lot of use even our own data with the South African Large Telescope. We do models fitting and stats and data mining, more model fitting. And you'll see these 2 last students here come from Madagascar and Mauritius, which are 2 of the SKA countries. So we've had a big influx of students from these countries. In fact, that's what I spend quite a bit of my time doing, is this kind of computing development in the rest of Africa. So if you're from any of the 8 countries listed there, you could have access to free hardware and training as part of our SKA readiness projects. You also have access to CHPC facilities. And here's my summary, where so the CHPC is our national supercomputing facility, big computers, lots of applications. The SKA is a huge radio telescope that is centered in South Africa, but will have parts in the rest of Africa. We're tackling lots of astro projects using Python. The CHPC is doing computing development in the rest of Africa. And please contact me if you're interested in any of these things, like playing around with the biggest computer in Africa. It's kind of cool. Or solving the mysteries of the universe. Okay, that's also something we do. And if you're interested in working in other parts of Africa, perhaps, or you come from other parts of Africa, I'd be really keen to hear from you. Thanks.
To end off tonight's talk, we have JP from the video team.
We might possibly have video issues. Let's see. You want to get some coffee or anything like that? It's working. Fantastic. Could be worse. Not yet there. I still first need to tell OS 10 where my screen should be going. But you know, we've started. Okay, so Stefano, that's the screen I was talking about.
Yes, there are options on it.
Why do you want options? If you bought a Mac, you don't want options. I mean, like, really, come on. Okay, so this is the talk now. I should just note to you that I kind of did this thing about, I don't know, like a couple minutes ago. So I may live patch my talk. Yes, so welcome to the video team talk that explains a couple of things. We are the Python Data video. I'm going to read it there and like you can listen. You've maybe heard of the video stuff, you've probably maybe heard of us. The 5 W's and the 1 H, can you, Jonathan, drop my level a little bit, please, I'm echoing. So what is it, why, when, where, who, and how? What is it? It's recording of all talks. It's recording of all talks done here in the 3 main rooms. And we also get the slides through this magical little box down here that I'll tell you more about shortly. It's in 720p, which I note because that's not a thing that actually happens generally. Usually it's kind of like analog video signals and VGA connectors, and that's just hard to do.
Or a camera pointed at the screen.
Yes, that too. Lighting on that is hell. So why do we do this? Because we've got some really cool talks, we've got some really great speakers, and you know, more than just these people want to be able to hear them because they can't make it, whether time, distance, ticket availability, or anything else. And of course, we can put them on the internet. It's not an exhaustive list. If there are more reasons, feel free to find some. When we're basically all the talks, I don't believe we've missed a single talk today. That does sometimes happen. We do sometimes lose talks. We haven't. Hang on, my firewall is shouting at me. When and where? All the main talk and tutorial rooms, not all the open spaces and such. Equipment availability, the stuff costs money, that's basically the main limitation. Who? A whole bunch of people, and thank you to those people that we suckered into doing stuff. There's a couple of you. The people that you know, Stefano there, he's the barefoot hippie running around. There's Potter Trapper, Kyle there in the corner. There's Graham. Where's Graham? Where are you hiding? Maybe he's getting coffee or something. There's Sikelo. Where's Sikelo? There, by the camera. And then there's me. Hello. How are we doing this? This is actually the fun part. So there's a bit of setup involved, there's a bit of equipment involved, there's a lot of wire involved, and there's a couple of adapters. Roughly, the model is based on what is used at DevConf. It's the 3rd one of these that I've personally worked on. It's about the 5th that you've done, I think?
I've lost track.
Okay. So there's a lot of stuff. There's a projector, there's a screen, there's a lector, and this is the lector, and there's video feeds out. There's presenter laptops, and then there's there's like a small computer in here next to the other small computer. There's cables everywhere. Then there's the other page that's got all the audio stuff that also gets into this. All of this outputs an IP video feed that goes to a switch and a computer over there. That in turn receives a cross mix of both this feed and the camera over there. We can live mix all of that stuff on there in picture-in-picture mode, side-by-side picture mode, full screen on the 2+ feeds. We're just doing 2 feeds, we can do more. Also audio cross-mixing, there's a lot of stuff happening over there. And the people that do that and don't freak out, like, give them an applause later or give them a beer, one of the two works. Like, that, seriously, there's a lot. There's 5 audio channels that they have to care about. There's all the feedback. This room is very echoey. There's the video feed itself. There's people's slides. I can just like do this thing and not tell him that I'm going to do it. He has to keep track of that. The people that do that, like, really, they do well. The core of the IP stuff is a thing called Voctomix. Thank you for the Germans, CCC, that started doing that development. They started doing that because they wanted something digital and IP based. That's the URL. The other one's actually a clickable URL, but you can't see it. The board in here, what I briefly refer to, is a thing from Tim Video's project. Tim is this guy in Australia that had a lot of money to throw his stuff, and he built this stuff, and he funded some development, and then that's URL for him. And this board takes in HDMI connectors and outputs HDMI and outputs IP video over MJPEG because everything's terrible. And so there's an actual reason. One of the video outputs is a USB 2 feed, and it looks like a webcam. Like, if you plug this thing into something, it looks like a webcam. The reason for this is USB 2 has a speed limit. Can anyone here tell me what the speed limit is? Okay, what is a 720p video feed like? 860 megabits. So what do? We make it look like MJPEG, and that saves a lot. Like, a lot, actually. I think that brings the size down to about 7. What goes wrong with this? Chromebooks don't like the video modes that this board can do. Rebooting the board is sometimes needed, as you saw twice in the last 30 minutes. Mode differences between outputs. There's a lot of video mode outputs. There's a lot of modes that your laptop can or can't do. Finding the right intersections there is tricky. These things aren't documented anywhere. VGA, yes, in 2016, some people still have VGA.
We haven't had any yet.
No, not at this conference, but it is still a thing on new laptops even. Different GPUs in your MacBook or your laptop has 2 different modes, even some of the cheaper laptops. The video on your one adapter is a different video interface to the other output. It happens. What else goes wrong? Software happens. We get random UI stalls. FFmpeg just stops writing stuff to disk. Why? If you know why, please tell us. We would like to know. Other recording pipelines aren't as well tested. We can't use the other one today because libav has a different symbol reference and it just isn't there. The capture board that I already mentioned, that looks like a webcam, and firmware. So this firmware is actually the one that we used in Pi, Ohio a couple months back. Why we're using it? We made it work there and we didn't want to touch it. So it kind of works.
There's a much newer version.
There is. We don't know if it works. This works. Are we done yet? No, we're not. Power can corrupt. Fortunately, we haven't had that. We had a very good event in this kind of thing. Audio levels. Echo in the room, voices, echoing, that kind of thing. Camera bumps. Someone stands up, backpacks, and oops, there goes the feed. There goes the camera. Just stuff happens. Batteries. Batteries. This room got hit once, I believe, already. Any of the other rooms? Anyone know? Okay. Cool. Batteries happen. Someone's laptop didn't work. We had to drop a desktop for video. This stuff happens. Running out of volunteers. Like, we have only so many people. It needs 2 to 3 people per room. Now, I would like to point out, as Stefano mentioned, he's got 20 of these adapters that he tried to do to find the way to do this accurately, okay? Sometimes this happens. And this is the one that works. Okay? The fact that any of this stuff works is sometimes a small miracle, but yeah, the outcome of it is you can see the videos on the internet, right? You can share these things with other people, and it's cool. And we would like to do more of it. So please help us if you can. That's it.